hopefully this is all going to work. Except we certainly don't want that to happen. And the microphone seems to be on. So we're just going to assume that this is all going to work and everybody's here anyway. Okay, so we were talking about separable differential equations, which meant that we could take all of the terms that have y's in them and put them on the same side as a dy, and all of the terms that have x in them and put them on the same side as the dx. And then we could just integrate each side separately using all of the techniques that we've been working with. Okay, so that was one thing that we talked about in 7.4. Another thing that we talked about in 7.4 was an exponential growth expression or equation where we had y0, which was whatever the initial amount was, and that was e to the kt. And k, if k is positive, then we have a growth situation. If k is negative, we have a decay situation. And so we can adjust it that way. And we did at least one example where we used a different base. So I think we had an example where we were talking about half-life and we had some initial amount, and instead of using an e power, we used the power of 2, and then it was to the bt, and we had to figure some things out. Okay? So that's just kind of where we are and what we were doing last week, because after all, it has been 5 days since we have done AP Calculus, and that's just kind of too long to not do AP Calculus. Okay. So we're going to move on to some additional examples, situations. And so let's talk about Newton's law of cooling. And Newton's law of cooling makes a lot of sense. It says that the amount of time it takes for an object's temperature to become equal to the surrounding temperature is an exponential function. So basically we have T minus Ts is equal to T0 minus Ts e to the negative kt. And I'm sure that this is all written down in everybody's journal. But T is the current temp of our object. At some time T. Ts is the temp of the surrounding medium. So if I'm bringing something in from outside, the surrounding media would be the air temperature. If I'm taking something and submerging it in water, Ts would be the temperature of the water. And T0 is the temp of my object when T is equal to 0. What's wrong with this? It's not writing very well today. And K is a constant. That's going to be, I don't know if unique is the right word. It's going to be associated with whatever the materials are. And as you remember from chemistry, is probably going to be associated to the specific heat. You're not going to have to figure it out. I mean, don't panic. It will either be something that is given to you or something that you will figure out in the problem because you have all of the capital T's and the time. Okay, but just kind of as a reality thing, you know that metals conduct heat better. So you're going to have a different K value if you're taking a piece of aluminum or copper from outside to inside than if you're taking a piece of wood, which is more of an insulator, or a piece of concrete. Okay? So it's just going to be different for different objects made of different materials. Okay? We got what we need. Again, this should have all been written down in your journals somewhere. So let's try an example. Let's do page 362, number 30. If somebody would read it for us, please. Rebecca, go for it, would you please? Okay. So I've got several times and several temperatures. So I'm just going to organize that into a little table because you know I love a good table. Okay. So when time t is equal to 0 and the aluminum beam is brought from outside into the workshop, what's the temperature? We don't know. That's what we're looking for. So that's a question mark. Or T0, which is something we're going to have to solve for. Okay? But in fact, I'm going to get rid of that T0, and I'll tell you why in a minute. So there's a time, what, T minutes later? Or, I'm sorry, 10 minutes later. And what do I know about the temperature of the beam 10 minutes later? It's 35 degrees Fahrenheit. And then what happens? So after another 10 minutes, or 10 plus 10 is 20 minutes, it's warmed up to 50 degrees Fahrenheit. And is there any other information that I know? Okay, so I know that TS is 65 degrees Fahrenheit. Now, it doesn't really matter what units we use for temperature, probably. The K value might look slightly different depending on what you use. But the big thing is to make sure that you're using the same units for all of your temperatures. So even though Fahrenheit is a stupid unit, it's consistent. Okay? And so, I don't really need to draw a picture. I have made a list of my knowns. What's the next thing that I write down? Oh, before the equation. I need a find statement. I know this is calc. I am fully aware this is calc. But we are heading into chapter 8, which is applications and word problems. And so perhaps we should take a little help from physics and remember things. So. I like that. So we want to find t at t equals 0. Okay, we're not going to use T0 because that's within the equation, and some of you are looking ahead and seeing where we're going to have to go. Priya. Excellent question. What about K? So if we go to the point where we write down the only formula that we know about this, right? And what is it? Ts minus T0 e to the kt. Okay. Oh no, T0 minus Ts. Thank you. You should, hang on, you should probably memorize that formula. I obviously haven't, but I will never take a test on this. Okay. All right, so Priya brings up an excellent point. I don't know what K is, and I'm going to need that. Okay, so instead of jumping right to the point where I'm using time t equals 0 as my T0, I could instead compare these two. And then I could let the temperature at 10 minutes be T0. The temperature at 20 minutes be my current temperature. And then what would I let little t be? 10 minutes. Because that would be the amount of time that had elapsed between there. What don't you like, Rebecca? Oh, really? You did this last year in pre-calc? Maybe? This particular problem or this formula? Like, well, it must be both, because the only way to solve, oh, that's, well, then, good for Ms. Mastracci to show to be working ahead. It's all right. It was a long time ago. Okay, so we can use the information between 10 and 20 minutes to figure out what K is. Okay, so if we substitute all this in, T is going to be 50 degrees Fahrenheit. TS is 65 degrees Fahrenheit. T0 is 35 degrees Fahrenheit. TS is still 65 degrees Fahrenheit. E to the negative K times 10. So don't get rid of your negative signs just because you think they're weird looking. Okay, so this is going to give us what? Negative 15 is negative 30, e to the negative k times 10. So that gives me e to the negative 10k is a half. So wait, what? Definitely, you're going to have to use natural log. So this is going to be the natural log of a half is negative 10k, or k is the natural log of a half over negative 10, which should still give us a positive number. Because the log of a half should be less than 0. Let's see if other people got the same thing. Sarah agrees. Zoe's digging at her calculator. Sarah, what did you get? Okay. Excellent, Gianni. Did you get it, Zoe? Okay. How about you, Zoe? Okay, so while calculus is not known for paying attention to units, let's pretend we're better than that. What should the units be for this number? Not Fahrenheit per minute. Just because it's a 9.8 meters per second squared is a constant. Okay, well, but this is a different kind of a constant. Okay, so well, no, it doesn't make sense because this is degrees Fahrenheit here and this is degrees Fahrenheit here. And when I divide both sides by 30 degrees, negative 30 degrees, this 1/2 has no units now. Yep, per minute. Because the argument of the E can't have a unit. So if time is in minutes, K has to be in inverse minutes so that they cancel. You can't have E to the 12 degrees or something. You can't do that. It's not allowed. Okay, so now we have K. So now we have a K value. And we can go back and now take t equals 0 and t equals 10 and let t equals 0 be t0 and t equals 10 be t and substitute it in all over again. Okay, but now we know what K is, and now we can solve for t0. So again, I've got t minus ts is equal to t0 minus ts e to the negative kt. Is that right? Yep, I got it right this time. So t is t of 10 minutes, and t0 is t of 0 minutes. Okay, makes sense? So T is what, 35 degrees? Minus the room temp, which is 65 degrees. And you could make an argument, I'm sure, with thermodynamics that the room temperature will change slightly when you bring something cold into it, but apparently we're not going to worry about that. The original temperature is what we're looking for. And the room temp is still 65 degrees Fahrenheit, e to the negative 0.0, what was it, 69 times 10. So this is going to give me negative 30 degrees Fahrenheit divided by e to the negative 0.69. I multiplied through. Think about it before you start complaining. And what do we get? Okay. Are we good? We got it? Everybody got the same thing? Okay. So the other problem that I want to do is another half-life problem. So let's do page 363, number 40. If somebody would read it for us, please. Whittier. Okay. So this should strike you as a growth decay type of situation here. One of the clues here, and I guess this isn't going to be an actual half-life problem. It will be related to one, though. One of the clues here is that they never tell you how much oil it gives out. They tell you, how do I know when it falls to 1/5 of the original value? Or when it falls to 75% of the original value. So when they're not giving you the amount, okay, that's one of the clues that you're going to want to use something that looks like this. Okay. So let's just remember that Y is going to be the output at some time t. Y0 is the output at t equals 0, and in this case, k is going to be the decay constant. Okay. So the deal with this problem is that they don't tell me what the output actually is. So I might call my original output, say, A0. For the original amount. And I want to find t, the time, for when the output is what? 1/5 A0, yeah. And you see, I hope, that if I substitute these in, my A0 is going to cancel. Because that's what they told us. We want to find the time when the well's output falls to 1/5 of the original value. Yeah, effectively. Okay. So what's K going to be? 10, because it's 10%. And that's how much it falls by. Okay, I've already included the negative sign up here. You could have written it as y equals y0 e to the kt and let k be equal to negative 0.10. It's up to you. Okay, but I knew that the amount of oil was decreasing and that I was going to have a decay problem as opposed to a growth problem. Okay, we good? Okay, so if I just write my formula again, y equals y0 e to the negative kt. My y is going to be that 1/5 A0. Y0 is the amount that I started with, and I've got e to the negative 0.10 t. Well, so my A's, let's just go through that one more time. My A0s are going to cancel, so it doesn't matter what that initial amount is. And that's one of those things, we come across this in AP Physics when they don't give you the mass, and you have to assume that if you follow it along, it'll cancel. And that's one of these situations here as well, where have faith and know that it will cancel, but it is kind of an indicator that you're doing this kind of a growth or decay problem. Okay, so as somebody said, this is 1/5 e to the negative 0.10 t. What are we going to have to use to solve this? Natural log. So I've got a natural log of 1/5 is going to be negative 0.10 t, or t is the natural log of 1/5 divided by negative 0.10. Have faith in your negative signs. And what do we get for a time? 16.1 years. Is that what you got, Maddie? Your hand was up first. I saw it. Okay. It's okay. All right, so we good? We got it? Okay. All right, so that's all of what I want to do with 7.4. Okay, are there journal questions from 7.4? I'm not going to start 7.5 even though we've got 10 minutes. I'm just not going to do it. Okay, so are there journal questions that we need to go over? Priya, I'm not done with class here, okay? And people may want their books. No, we're good. Everybody's good? We took the 7.1 to 7.3 quiz, right? Did I give it back to you? Okay, I think I graded it. I'm pretty sure I graded it. Hang on. Let's